Welcome to Behind the Curtain Wall, the series where we explore the systems, standards, and stories shaping today's most resilient building envelopes. Today's timely conversation cuts through wind-related headlines and half-truths, discussing code requirements, actual facade damage from wind events, and the disconnect between perception and performance. I'm joined by Jon Medina, founder and principal of Miami Curtain Wall Consultants. As you may know, Jon has spent decades in the field consulting on glazing systems, waterproofing, and structural envelope performance on some of the most complex projects in Florida. And we're thrilled to welcome Dr. Jon Galsworthy, engineer and managing director of CPP Wind's Canadian office. Jon is a globally recognized expert in wind engineering with more than 20 years of experience analyzing wind loads on tall buildings, long-span structures, and city-shaping developments around the world. Together, Jon and Jon bring perspectives from the field and the wind tunnel to help us better understand how facades are designed, tested, and challenged when wind becomes more than background noise. So let's jump right in. Jon, thank you for joining us. Could you give us a little bit of background of what you do and what CPP Wind does?
Yeah, thanks, Daniel. Nice to be with you and good to see you again, Jon.
Thank
Yeah, so CPP Wind Engineering, we're a specialized consulting engineering company, and we look at any issues related to wind and how the climate in general affects design. Design of structures, design of buildings, design of anything in the built environment, really. So my specific area in CPP is looking at buildings, but I have colleagues that look at other aspects on buildings, including air quality, other structures like transmission structures, or even something what seemingly straightforward as a solar panel. So we cover kind of a broad range of areas, and anywhere where the wind impacts the built environment, that's where we fit. Helping clients, helping owners, helping building officials, helping other design professionals understand and account for the impact of wind and snow and other climate matters on the built environment.
Excellent. And Jon, Jon Medina, you talked about your early experience with wind tunnel studies. How did that shape your view of code and testing today?
So we've when I began my career, I started at the Construction Research Laboratories as a test engineer. We would receive from around the world wind tunnel studies. I was a young man. I was probably 26, 27, 28 years old. And I would have to determine the wind pressures that we would test full-scale mock-ups, curtain walls, and we would test for the full-scale effect of the wind tunnel studies. So I was always keenly interested because the performance, the lateral stresses on the curtain wall really depended on what these wind tunnel studies results were. And in the process, have been involved in talking about that a great deal, even still today in regards to, it goes back 40 some years. So even today, we're constantly talking about wind speeds in regards to hurricanes that have impacted, especially lately, the West Coast.
Right. Now, diving into the wind speed claims, you often see wild wind speed claims after a storm, and now as we're approaching hurricane season, it's more relevant than ever. Why do those numbers usually miss the mark?
Yeah, it's a good question. I think it's kind of a complicated answer, maybe complicated a little bit by the intent of the message. Maybe that's maybe one way to say it. I think if you're in the shoes of say the National Weather Service or a hurricane forecaster, they're looking at the winds and the formation of the hurricane, say on the west coast of Florida out over the Gulf, east coast of Florida, South Florida out over the Atlantic Basin. And they're looking at the wind speeds that come out of the model over water. We also know that from an engineer's point of view, more interested, engineer, architect, and design professionals, more interested in what's actually happening at the site, that they're concerned about. So there's that mix of audiences, mix of messages, not so much around the technical or the actual wind speed, but maybe the time and point of the storm. As the storm makes landfall, it starts to lose some of that energy source, which is the warm water, and that wind speed quickly decays, I guess is a technical term, as you make your way, as the hurricane makes its way inland. So we see that, in kind of looking at the storms and the wind speeds observations on land. They often don't line up very well with what was reported just leading into the storm. That's at least part of the reason, that we've got this mix of where it's reported, before it makes landfall, it's out over water where it's getting that real energy source, versus on the land where it's actually making the damage. And at that point, it's already losing some of its strength.
And how do
Well,
engineers usually define and measure? Oh, go ahead, John. Sorry.
No, I wanted to comment. I thought, John, on a very very practical level, it's like, the notion of who is interpreting the information, I think is really kind of at the key of it, because the design professional is really taking into account what is the potential recurrence of a specific type of storm in a period of time that the building is going to be constructed. It's not quite the same having a building that your anticipated life is 100 years versus 1,000 years. So the recurrence of that storm, the percentages change based on the anticipated life of that building. So I think that's one aspect that I think is the kind of key, is to, well, if a designer looks at it from a different standpoint than perhaps a insurance adjuster, who perhaps has a different perspective of what kind of wind he needs to be able to project, or that someone can forecast, or that may have occurred during a specific incident. And so one is a very broad approach of talking about wind, and the other one is a very specific item associated to a specific narrative that has to be made in order to maybe take benefit or take advantage, or not, or do the right thing by a property.
Right. And you had mentioned something last time we spoke, John, about damage blamed on storms that doesn't really line up with like real world effects. Can you share that example of the when reality and the height don't really match up?
Right. So I think that when you think of if you kind of if you get very basic about, and I'm gonna talk about it in a very sort of practical way. There's this boundary layer where our buildings are being built in, right? And if that and that boundary, we really don't care how high the wind is above. For an architect, maybe a aerospace engineer, it matters, but for us, that boundary is about, and I'm going to sort of exaggerate to kind of super high rises, 1,200 linear feet, and that's the area we're interested in. So if the boundary down at the ground has wind, you could expect a certain degree of wind, but that wind that's up at the top of the boundary above the building, if that wind is the one that you project down on the ground, it would be very, very destructive, right? But way up high really doesn't do anything at all. And I'm talking kind of I'm trying to be ambitious to get all the ideas across in short order, but at the very bottom, you have a lot of little buildings, a lot of canopies of trees, you got cars, so you have a lot of friction, and it breaks up that force that could be on the ground. Right, as you go higher up, where there are mid-rise buildings, there's a little bit more higher pressure, and then further up, where you have no friction, there's higher wind speeds. Oftentimes, and for us, the kind of threshold height off the ground is is pretty much plus 30 feet. That's where we kind of determine what the wind speed should be. Oftentimes, you'll hear some people talk about wind speeds and say, well, there was a static 200-mile-per-hour wind that was clocked. Yeah, but if it's clocked 1,500 linear feet off the top of the, any buildings, it doesn't do anything. But if you say that there was a static wind of 200 miles per hour, 10 feet off the ground, it would probably erase all the buildings, that are in its path, right? So, there's this sort of kind of mystery aspect when people are talking about wind speeds. It's like, look, you don't have 200-mile-per-hour winds out there every day, because they're entire small cities would just be eviscerated. And so, after a while, and I, and I don't look into it as much as I'm sure John does, but after a while, by looking at enough studies, you kind of know where the sweet spot is of a tall building, what the pressures ought to be like, right? And so you kind of already know that, look, about 20 years ago, wind speeds, varied. The high lows were a certain speed. After a hurricane, it sort of increases. It goes down a little bit after. There's this sort of pattern that happens. And we have to kind of live within that as designers, understanding what to expect.
Yeah, I'll expand on that a little bit, John, if that's okay. I mean, you did a nice job talking about the friction and ground effects and versus, winds up high and, and I've seen in my career, folks kind of, as you're implying, is pick numbers to fit narratives, maybe.
Mhm.
But as building codes and our practice as wind engineers using wind tunnels, I mean, we take all of that into account. I mean, when we do a study on, say, and again, let's focus on the built environment, right? If we're designing a new building in South Florida or Miami, say, or on the West Coast of Florida, I mean, we take great care to model that carefully in the wind tunnel, and maybe just for your viewers that don't have never experienced what a wind engineering wind tunnel looks like. It's not you might have a kind of a picture in your mind of a car in a wind tunnel, like on a commercial with nice streams of smoke going over it. And it's the same kind of concept, but with different intent. We build actually, model of the city, within a certain radius. And if you've seen a picture of, like, imagine kind of a 10,000 foot or 20,000 foot view of a city, and so we're modeling that in the wind tunnel. We're getting all of that turbulence, all the friction effects modeled appropriately, and then we can look at it from a kind of design scenario. So, John, you mentioned 200-mile-per-hour static wind. I mean, that appears nowhere in any code.
Yeah.
It is that 30 feet off the ground, and what's the gust wind speed? So there's, and then that works into an engineering model, and over the years we've gotten a lot of confidence in that. And so when we're say we're doing a report for John's company, they'll have a good idea based on experience. Well, we can come in with a very detailed study and say, well, experience matches up quite well here, but in there's maybe an architectural feature that's causing a little bit higher load or lower load or something like that. So it's a very, very well defined science at this point, and engineering practice. And so, back to the question of wind speeds, I mean, we look at it from any number of angles. So we can look at it from, sometimes we're asked maybe to say, okay, if, like, what was the simulation of a recent hurricane? What did that actually do to my building? We might have someone that we've worked for in the past, and they come back and ask us that question. Looking at the buildings under construction, recently constructed in Miami, they're really pushing new heights. 1,000-foot building in Miami, in that wind hazard, highest wind hazard in all of North America, is a very significant endeavor. And so we're looking at that. What's 1 in 1,000 year wind, 1 in 2,000 year wind. We're looking at that from that point of view. So, and at that point, it's more of it's really a statistical model. It involves a lot of meteorological science, a lot of statistics, and a lot of fields that kind of come together to really paint that full picture.
And you mentioned in our last conversation that your model includes over or 300,000 storms. Is that right?
Yeah. So the model we use, it's so if a designer were to go and look at the say open up the code book, and so if they look in Miami-Dade County, the design speed is 175 miles an hour. Okay, well, that's based on a lot of science, as I said, that's input into that. What we do is we take that same science and we drill into a very specific site. And so yes, it's actually 300,000 years of simulated hurricanes, and yeah, we're digging into it and looking at the impact of each one of those simulated hurricanes as it goes past the site. So it's taking what at the code level is more of a broad view and dialing it into a very, very site specific, and everything that's contained in that, whether it's surrounding buildings, whether it's surrounding terrain, all of those impacts.
That's fascinating.
The one of the things that and we've been talking about it from the standpoint of design, and some of the subtleties are, well, for example, the Florida Building Code, which is a very worthy code, that is the model for a lot of the things that's happening in the Caribbean and South America and so forth. For the most part, it has the designer has the ability to use the code and select and select that methodology to arrive at the design loads for wind. And ordinarily, the wind tunnel predicts a much more site-specific and accurate set of loads that is usually lower. And so there is value in doing wind tunnel studies in advance, because if the solution is so prudent and so conservative, oftentimes you have to spend a lot more money in structure and glazing and all the rest of it to withstand the higher pressures that could be expected from the Florida Building Code. So the wind tunnel study and what Jon does is extremely important, because you could save maybe 15-20% of the cost of a, and I'm being kind of general there, but 15 or 20% the cost of as a result of predicting or forecasting what the more actual pressures may be based on the potential recurrence. There's also another aspect that, and you've seen this in the movies, where someone is, there's a high wind in New York or something, and someone is walking down the street and suddenly they turn the block, or it's raining and the person slides 20 feet because the wind gust turns the corner and creates a vertex and it pushes the person along. And, it's kind of like when that happens to you, it's like, wow, what just happened? That's like just an amazing feeling. The wind carried you through, and sometimes people fall and break something, right? So the other aspect, one of the other reasons why, especially in an urban setting where you have a lot of tall buildings, you have these sort of bowling alley effects, is to check that you don't have this sort of buffeting effect that can happen around a corner or intersection. And certain building geometries and their angle and their angle in the city can, in effect, increase the velocity of that wind as it goes through, almost like in a bowling alley, right?
Right.
The buildings create this sort of funneling effect, and you get these sort of freak winds that these sort of gale events that happen. So that's another reason why the wind tunnel study is important, because you can factor in that safety. The safety factor around the perimeter of the building at their lower level, for example.
So, Jon, with that same train of thought from your experience, how do developers or architects interpret or misinterpret wind pressures when designing facades?
That's a good question. I mean, in my experience is generally working with pretty top-notch teams. So, in my being part of owners that bring us in, that they're usually the same kind of owners that bring in great folks like Jon's firm and good structural engineering firms, and good architects. So we're usually exist as part of a team. And so that's already got that inbuilt sense that the owner is thinking about what's best for his or her building, but also takes these issues seriously. So I haven't seen too much in my career where folks have misinterpreted. I think at least in the design scenario, in some forensics, if you're looking at things from what we're talking about before, a little bit on after a storm, or trying to interpret one thing, and if there's I don't want to cast aspersions here, but if there's a certain narrative behind someone's storyline, then often that can get bent a little bit. But on the whole, as far as a design community, I think it's at this point, certainly South Florida, it's well established, and I think certainly on the East Coast and new buildings on the West Coast, I would also say that are built within the last 20 years, maybe. I don't want to put too fine a point on it, but certainly as the codes have evolved, those buildings have performed quite well. I think the storms, maybe just expand on that a little bit on the recent storms. Those storms have come aground in areas that hadn't really seen significant storms in quite some time, and they weren't at the time of construction built to the same kind of standards as we would do things today.
Right. And then I think, moving on to those post-storm kind of claims, what are some of the common misunderstandings around like water infiltration or minor damage? That's something that we talked about a little bit before.
Yeah, this is a little bit beyond my expertise, but my understanding is, the building envelope, windows in particular, they're designed to, at a certain wind speed, then those seals will start to allow some water in. So that's one thing. I don't know. I haven't had any firsthand accounts or been involved to see what that looks like in a building where the envelope is otherwise intact, but it's had a little bit of leakage through windows. I have heard through colleagues, if there have been major openings in the roof in particular, and water gets in, then that can be just quite significant. The mold sets in quickly, but I don't know what that does ultimately to the long-term structural performance. But anecdotally, at least, and that's where you get quite significant. So if you get that initial cladding failure, whether it's on the roof, whether it's in the building envelope, otherwise on the walls, then at that point, when you can let a lot of water in. The building lets a lot of water in, and that's where you run into those issues.
So to kind of maybe just go back to the whole wind speed issue, and wind pressures. If I were going to tell you, look, in the last 20 or 30 years, if I were going to tell you what the wind speeds that have been for tall buildings, what the wind speeds generally prove out to be through wind tunnel studies, without the privilege of doing the wind tunnel study with John, okay, but generally, as being able to talk like an old timer, I would tell you, look, plus 100 PSF, minus 100 PSF seems to be the threshold. All right, with some hot spots on a building. So what does that mean? Well, you could equate that to a stagnation or a wind pressure of a 200-mile-per-hour wind. Okay. And so what happens is that most designers of curtain walls that want to sell product has to test their products at a laboratory and pass tests that they pressurize those curtain walls in a positive direction and a negative direction. That's where John and I sort of interact at that point where, okay, so what's that pressure that came with the wind tunnel? Well, when I do the math and I put a volt of I establish what the wind is on an eastern or north or south or west elevation. What is that wind pressure? Which is the highest one? You test to that and you figure it out. When all things being equal, a tall building will oftentimes be within that range, plus or maybe plus or minus 15%. Where, and then so as you go along the corners of the building, the top of the building, those zones take a different type of force. It's a higher pressure, and so you take into account that look, you're going to have some high areas, and so you design for that. And it's interesting when you've been doing that for a long time, and suddenly a hurricane comes along, and now the wind tunnel study comes back and you have a wind that says it's 240 miles per hour. Hey, it's kind of a neat idea. Nobody's really clocked it at 240 or 250 because nothing can stand up to the force of that. And when I say the force, don't think as a static stream of air for a minute. It's gusts back and forth, positive and negative. Yeah, so sure, you could come up with a force of 240, 250, but the problem is that we don't have all of a sudden you have to go back to the wheel again and invent a system that can meet that wind load. And then the designers will turn around and say, are you crazy? How are we going to do it? We don't have anything in the marketplace. You're making us look bad because now we got to reinvent the wheel, right? So there's this really great dynamic that happens when all of a sudden, yeah, you could raise the threshold up a little bit, all right, but you can't get out of what is reasonably which is what is reasonable to build, all right. And I don't know if that makes sense, but if you raise the wind pressure, then you're all of a sudden causing a real domino effect in the industry because nobody's tested for those things, right? So, there's been times where, I've looked at the wind tunnel study and I've said, listen, we got to take a look at this again, all right? And I've made the back channel call and I've said, look, do me a favor, reanalyze this little area here. It's not adding up, right? And then you kind of talk through some of the things and I think that engineers and architects that are versed in this thing, they're reasonable, they're top notch, they realize the potential safety issues. So it becomes at a very high level, the conversation. I'm glad you brought that up. It's not a conversation for just anybody that just follows, the letter of the law, because a lot of this has to do with probability. And I think that, John, you spoke about that very elegantly the other day. What is the probability of something happening? You're still spitballing at the thing, right? So it has to be responsible interpolation of all of this wind analysis that happened in the 300,000, right? The number just can't suddenly jump up. It doesn't really like, a sharp line straight up,
No,
right?
yeah. No, so maybe to dig into that kind of scenario a little bit. I mean, I'm glad you brought that up, John, because we, when engineers, we're looking at something very technical, very bespoke, but we all know, like those of us that have been at it a while, we know we need to, fit in the broader design question. And so, yes, everything is in, so we're looking at the physics, we're looking at particular features that might cause it, but we also have to be realistic. And I think any engineer who's looking at their work carefully and reasonably, they have that mindset, and so the way I talk about it inside the firm when we're working on projects is, okay, we found a high result, say, let's actually unpack that. What is causing that? And then put it in the context of, okay, and maybe just to get super specific for a second, like our instrumentation. So we measure it with a tap on a building. So that might be the size of one light on one window. And so what's the consequences of that? I'm not saying we're artificially lowering the load either, or the pressures, but there's that back and forth. There's that discussion. How does this get built? What are the consequences? I mean, one thing I've had conversations with folks in John's field is, okay, what's actually driving the the issue. Like, is it the deflection of the glass? Is it the stress on the glass? Because those are different questions as the wind sees it. And so we've got that nice dialogue back and forth and professional respect. And I've learned a lot from those conversations over the years and understand where our work fits in. And I've had an education more than once on what's the NOA process in South Florida. But it's important, as John's saying, to to come to the table with your best knowledge, your best information, but also that it is a broad question in some uncertainty. So you're looking at it from different angles.
I'll just add, and you brought it up, and about taps and tab on when they build a model, they model the project that they're going to forecast possible wind pressures from. They scale the model down where the wind is takes into account that the scaling down of that model, and the models are these like really cool objects that are like so very, very precise and perfect. And they actually include them in their wind tunnel studies so that they could. It's like proof of theory, right? They show the model, and the model is on a turntable, and they move the turntable to in the direction of where the wind is coming, so that you get northeast, southwest, all the different angles, to find those hot spots that we were kind of talking about. And then that kind of plexiglass model that they have, they drill through it these little ports that are like these that they wire up with sensors. Like if you're doing an EKG, right? And so you know how an EKG works because you've probably had it done to you. So well, it's kind of so they insert these little wires all over the place, and it's like, to me, it's like the coolest technology. Because if you're an architect, you like making little models and things like that look like your project. And one day that model is going to be a high rise. Don't get me wrong. Yeah. Scaling up and scaling down is a really kind of cool thing, to see something what looks very small that eventually will become, a super tall building is really it's a really neat thing. And then those sensors are throughout, and they're able to capture this scaled wind and create this this analysis, which is really invaluable in everything we do. And there, and we've had clients who are not, that are first time clients, and they don't understand why they have to spend $100,000 or $150,000 in a in a wind tunnel study. To give you an idea, it's not cheap, but when you're planning a $500 million project or a $250 million project, it's a drop in the bucket as to what it's going to save you. So you kind of look at it from the large, the kind of the bigger perspective, that there's an enormous amount of savings, and you're designing specifically to those loads, not made up loads, but loads that you've been able to forecast. And I think that's scaling is of a model, and the wind in a model is one thing. And then there's that kind of that concept of projecting or forecasting, and maybe not necessarily forecasting, but after a hurricane passes, right? There's the that you've seen it on TV, those wind tunnel, those not wind tunnel, but those airplanes that go into the storm. Yep. They measure the storm 30,000 feet up in the air, and then they scale down what they think the wind is, which is another way of looking at wind. It's just not the way we look at wind, right? And that in itself is an entirely interesting conversation as to how those guys think. It's like, in hindsight, they come back and say, well, the wind had to have been this, and then at this specific site, at this specific moment, I'm going to extrapolate and kind of come up with their simulation that the wind had to have been a certain a certain pressure. And so that's always sort of interesting how people get to that place and call it science.
It is. Now, I want to shift gears a little bit to some of the conversations that we were having last time we spoke, which is the whole psychology of glass and a risk, and how people like to watch hurricanes through their floor to ceiling glasses. How has glazing performance changed public psychology on that?
I mean,
John, you
yeah, sure, I can start. I mean, when Jon mentioned that when we were chatting earlier the other day, I wasn't quite aware that that's it's become that much of a thrill-seeking sort of thing.
People have watch parties out here.
Yeah, I mean, as an engineer, it's a little bit like the Little Red Riding Hood kind of question, right? When is it going to be too much? But I think I mean, that's in some ways, in a strange way, it's almost a credit to the design industry that that everyone has that confidence. And I think it's also a measure of the evolution of the codes, right? I think there was when we look back at when I was starting out my career, um, there was a lot of damage in hurricanes due to debris, and flying debris, and it would impact glazing and break that glazing, and then that would lead to the damage that we were speaking about earlier, not just water but also wind related. And Jon, you probably know better than I do how long the impact resistant glazing and envelope has been part of the code, but it's quite some time now.
Yeah.
And so I guess it's the confidence of the public is reassuring, but also terrifying, because, and I'll just say it this way, is that it's been a long time since at least Miami has seen anywhere close to its design hurricane. I mean, the one in certainly in our memory was Andrew. But I guess Wilma was the next one of note. I think that had some damage with it associated with some roof gravel, so that led to a positive change as well in the codes. So yeah, I'm not quite sure how to respond. I mean, it's being a bit of a thrill seeker myself, sounds kind of fun, but also as someone responsible for quantifying and specifying what the wind demand is on those pressures. I mean, I'm not sure I would advise it, but anyway, it's interesting.
Yeah,
The psychology of it is all fascinating. Yeah.
I think that I listened to a lecture by kind of like a colleague in this sort of forensic industry, and the fella had been studying John. It was really kind of funny. The guy starts with, "I'm an expert in air." I said, "I'm an expert in air entrainment, and I've been studying air entrainment for the last 30 years in concrete." And he was a doctor, by the way, and he was and I'm trying to think of his name and it escapes me, but the guy says when he says that, I said, "I think I'm an expert in water." If he's an expert in air, I'm an expert in water. And then I started to think about, boy, I think I know a whole lot about wind because I felt wind a lot, right? I've been through like major hurricanes, and I could tell you what 25 miles per hour feels like, right? I could tell you what 70 mile per hour feels like, right? We rode into last year. There was the no-name hurricane. I call it the no-name hurricane because the media didn't come back and correct itself the next day that the wind speeds were clocked pretty much throughout at about 85 miles per hour, which is the first level. That's the lowest level of a hurricane. And so as a result of that, there was one of the buildings was leaking that we were working on, and they called us about 9 o'clock at night and says, "We don't understand why it's leaking. Can you come out and see it?" The news said there was a flash flood situation. I said, "Well, there's not many floods. I can't see that becoming an issue." So I got in my car at 9 p.m. at night and traveling from the land side to Miami Beach over the bridges, and now I'm on my second bridge, and I realize I'm in a hurricane when my car is starting to lean away from the wind. and all the palm trees are almost bent completely. I realized that I was in a situation, and so we got to the building. We go up to the top of the building where the people were complaining more about this water issue, and I could see through the glass the palm trees. The palm trees are totally flexed. And I'm like, it'd be interesting to go out on that rooftop and see what's going on out there. Let's face it, I'm already here. I might as well go feel this thing.
Mhm.
And I'm going to tell you that I know that wind in that area was clocked at about 85, and I'm 250 pounds, 6'4", and I went to the door and I tried to go through that exit door into one of the stairwells that doesn't have protection, and I couldn't open the door. Couldn't open it. I was leaning entirely into the door. The other architect that did the same as me, that drove to the island, to Miami Beach, was also terrified because we had just gone through a hurricane, right? And so I said, listen, film me, because I want to be able to record that at 85 miles per hour, you can't open a door because that positive pressure is forcing it. And those are kinds of experiences that when people are talking about wind speed, you almost sometimes need to physically know what that is. I ran a lot of tests at the laboratory where we were doing, we were maxing out over 200, 140, 160 PSF, positive, negative loads for plus 10 seconds, plus 15 seconds. Some of those loads we would run to destruction. What's the highest pressure before where we would peak out, right? And so, I've seen a lot of things break or explode, and so I got a sense of what it looks like. And so as a result of that, you can kind of now see when someone shows you the wind charts or the graphic representation of the zones on a building, what the pressures are, and then you can you have a sense of the orientation in South Florida, especially Miami. I already know that the high wind comes from the southeast during hurricanes, because the winds usually come in through Hurricane Alley. And it has that name because that's where maybe 100,000 of those storms came in through Hurricane Alley that head towards Okeechobee. All right. And so there's a path. That's why it's called that. Well, those other winds kind of spin off, but that's where Hurricane Andrew, all of that damage happened, and because that was Hurricane Alley, was going through Hurricane Alley. There's been a few that's gone up the coast, but that wind usually affects the buildings on Miami Beach the worst.
Yeah.
On the southeast side.
Yeah.
Right? The southeast corner gets hammered. And so there's this sort of realistic understanding of it. It's no longer an esoteric sort of thing. It's kind of like understanding what should be happening academically, what should be happening. Maybe it's not a good maybe it's not a good idea to have an outswing door at the southeast corner on every floor of a super tall building, right? At the corner. And so you have to go back to the designer and say, well, maybe that should be fixed glass or a wall. And let's put the window on the other side where you don't have to get to it, right? Because there's a general understanding that that's going to get brutalized every time a hurricane comes through South Florida. It always does. Wilma, Irma, Andrew. Now, Andrew was a hurricane that you didn't have that many tall buildings, so the destruction was kind of at the lower boundary. The two-story houses that got beat up pretty bad. But now we actually have a culture of people that are comfortable in glass boxes on the beach. And they believe that, they could be safe watching the hurricane come, and they buy because they don't want any metal in their glass. They don't want any walls. They want to be able to see the ocean, look down, see the sharks swimming amongst the people. That's kind of they don't want to get hot, so they would rather see all of that from inside, and so we're here saying, look, within reason, you can do this. Okay, it's okay, we can do this, But maybe you want to stand away from the glass when the hurricane's coming.
Gotcha. Now this has been interesting. The two sides of the story, one from the wind tunnels, and then out in the field, like you, John, have been in the middle of a hurricane. Um, I'll ask you, Dr. Galsworthy, first. What do you wish developers or designers or even attorneys understood about wind loads and code requirements?
Yeah, it's an interesting question. I think if I wish they understood that it's more than just a simple answer. Maybe that's the way I'd answer that. That it's not just
Yeah,
pick one number and then thinking that you can understand the full picture. And that's kind of the theme of what we're talking about here today, where
right,
it's you know um, trust the experts. I'm pretty fortunate. They work with folks, as I said earlier, that if they've made the decision to bring me in, I know that we're usually working with folks that understand the issues. Um, and I would just say also, maybe not exactly to your question of what they understood, but and I think this is generally the case, but take the issue quite seriously.
right,
It's not something that you know, especially in Florida, it's the highest wind hazard, as mentioned earlier, in all of North America. We've got a history of these of hurricanes. Codes can do what they can do, but there's always things to learn. Um, I've got other colleagues that spend time in other countries that don't take it seriously, or their codes have, maybe that's not a fair way to say it, but their codes have not caught up. And that the construction practices and the building codes and the actual demand, the wind load that they have to design to, leads to some real catastrophic issues. And it's not very far away from Miami. If you go to, and there's been examples, I can't remember the exact hurricane, but just in the last few years, there's examples of new buildings that underwent severe damage in hurricanes. So when come back to your question about whether it's the owner, whether it's the lawyer, whether it's or any other relevant party, the keeping keeping the building intact in the hurricane, the folks you've hired are they we think long and hard about these questions and the complexity of it. And so when we and other things that we said before, when we come with a recommendation, it's always a well considered one. Good question.
right.
I haven't ever been faced with it directly with an owner in front of me, because usually our studies are again, as I said earlier, part of a bigger team.
Right. No, I mean, I think we like to bring up these kinds of questions because, with this series, we'd like to try to see how we can inform the industry a little bit more, and having this space gives us that opportunity to do it. John, what are your thoughts on that? How would you see, um, how would you wish to, developers and designers and, you know, how would you want them to understand, wind loads and code requirements?
I think it's been my experience that dealing with developers and down the line with architects and other consultants and so forth is that um you you that and in this space of design, people just pick up the variables and they insert those variables into the equation and they spit out an answer, and it becomes really streamlined because people know what to look for, and there's not a lot of the sort of the emotional baggage that goes with, well, if this fails or it doesn't. It's like you have a sense of what's right or wrong and what does it meet the smell test? Is it reasonable, right?
Right.
Um, I've encountered projects where I felt that the wind pressure was wrong. It was just way too high, causing an enormous expensive process to comply with that. And we managed to do it, right? We managed to do that, but did it really truly need to be all of that effort? And it was what it was. It was, at some point you have to you take the problem and you you take it apart, you sort of put it back together and say, well, we can still go ahead and do it, meet the requirement, and so forth. So I think that at the higher level of thinking amongst experts, there's no romanticism about it. Or there's you don't start to think about the drama that could happen if something fails or not. It's like it should be fine. You understand it that way. I think once you get out of that space, and then now you enter that space of, well, what happened after a storm or a hurricane or a wind event or a seismic wind event, you know, um, at that point you start to ask the questions, well, did you have a systemic failure, or did you have like a tree trunk go through a piece of glass that took out, created an aperture, and that aperture was so large that it took out, all of the utilities. And I like to give the example of the Titanic. The design pressures and the design are all about keeping the ship afloat. It's not really about whether or not your photographs and your frames are going to get wet or not. It's
Mm.
you're trying to keep the hull together so that all of the utilities inside the hull of your ship continues to work, and the ship propels itself through the ocean, and it doesn't sink, right? And so what we're trying to do is get a husk or an envelope that could withstand those pressures, that there's not going to be a systemic failure as a result of the wind, that can cause these apertures to happen during an event. And then the building is exposed to all of the wind and rain, and the roof blows off, or the wind goes through from one side of the building to the other and opens up a hole on the other side, makes the situation worse. And I've seen that. I've actually seen that where a couple of lights of glass have broken
Yeah.
on the east side of a building. The wind has taken out all of the demising walls inside, and has come out the other side and broken out the glass on the other side, on the 20th floor of a building. Now, why did the first two lights of glass broke? Nobody could really say, but the amount of damage on that one floor was enormous on a Class A building, right? Um, and so that becomes a whole lot more dramatic. All of a sudden it's like, wow, those are the types of things that you say when an unforeseen condition happens or a God event happens. There's no stopping it. And so you want to avoid that. And I think that that's what we kind of we try to do together, from different perspectives, different angles, right? And we all have to sort of rely on each other's expertise to make sure that we're getting it right. We need each other. If I don't provide feedback back to Jon, or Jon doesn't provide me feedback, we're not. We know that we're there working at the problem from a different angle, trusting each other in what that information is going to provide us, right? So it really is a collaborative effort.
Agree 100%. No, that's on my side, that's the joy of the work. It's you can do the technical work is one thing. It's interesting, it's challenging. But at the end, it's seeing something get built, and that that you've got an owner that's has the confidence in the work that we've done. That if an issue has come up that causes a challenge, we approach it with the right mindset. And deeper relationships come from it, and you learn a lot. So that's truly the enjoyment of a professional design career for me.
Yeah, absolutely. I think that brings us to the end of this episode. A big thank you to both of you, Dr. Jon Galsworthy and John Medina, for an insightful conversation. One that not only debunks a few wind myths, but also grounded us in the realities of design pressures and performance expectations, and the role that the rigorous testing plays in getting the facades right. If you enjoyed this episode or learned something new, be sure to follow Miami Curtain Wall Consultants here on LinkedIn and our social platforms. And check out CPP Win for more about their advanced testing and modeling that helps engineers and designers build smarter. Until next time, thanks for tuning in to Behind the Curtain Wall.